Okay, Bismillah. Okay, so let's continue our discussion. Okay, so this will be my second video, and I would like to continue discussion the topics on measurable function. Okay, before that, let us recall what the meaning of definition. Okay, let us recall what the meaning of measurable function. Okay, so supposedly we have two measurable space. Okay, this is our first any measurable space, and the second one we have the specific measurable space. Okay, and of course we will consider a mapping, a function, a function that maps from our set X to the set of real number. And of course we say that from the previous discussion, such a function is called measurable. It's called measurable if satisfies such condition. If we consider all borrowed set, then the pre-image, the pre-image of all borrowed set, so we can find we can find pre-image of all borrowed set inside of our algebra or sigma algebra. So therefore we call it, our function here is measurable. Okay, so in previous video I already discussed two examples, and I already showed that some function is measurable and some function is non-measurable, which measurability of function depend on the choice of our algebra or sigma algebra. And then I just give you one home task. If you remember that I asked you to try yourself to understand how from this function, try to check this function is measurable with respect to which algebra. Okay, so today we will I will continue our discussion on the still we will discuss the same topic, measurable function. So let's use this one. So the video is recording or not? Okay, let us recall. Let us recall what the meaning of indicator function. What the meaning of indicator function? So this indicator function have been introduced by Prof. Nasir in his lecture. So I just want to recall what the meaning of indicator function. Okay, suppose we have any set. Let this set let be X here be any set. And then from this set we can have a subset. Subset of X. Subset of X. Let be A is a subset of X. Of course we have a lot of subset of from X here. Okay, so now Okay, so now let us recall search of mapping. Okay, with this notation. Okay, search of mapping with this notation. Okay, that maps from x set of the set x into the set of real numbers. Okay, so this is just a notation. Such of notation here is a mapping, okay, or it's a function that map from the set x to the set of real numbers. Okay, so we have something like Greek letter of x, and then we have a. What is the meaning of this a here? A here we consider a subset of x. Okay. Okay, of course, such a function. Okay, such a function here is called indicator function. Okay, indicator function. Okay, or some textbook, some textbook, they will use characteristic. Okay, characteristic. Okay, characteristic function. Okay, so either indicator or characteristic function here just give the same meaning. Okay, the same meaning. Okay, different term but same meaning. Okay. Okay, so now such of mapping that map from x to r is called indicator function. Okay, so this function, okay, is called indicator function, where it's defined by where this function is defined by this one. Okay, it's called okay. Maybe okay. Okay, it's called. Okay, it's called. Okay, I will use the word indicator. Okay, indicator function. Okay. So now such of indicator function is defined by this one. Okay, so now we have x. Okay, of course our x here should be all element of x. Okay, so this one will give us two values. Okay, two values meaning that we have y if okay, so indicator function is always give two values. Okay, 1 and 0. Okay, 1 and 0. If okay, so such a function here is equals to 1 if my x here, okay, is element of a. Okay, when my x here is element of subset a, then this function will give me the value 1. Okay, and then this one is equals to 0 if my x, okay, is element of the complement the complement of my subset a here. Okay, or either one. Okay, or other meaning. Okay, in other words, what the meaning of x is element of a complement here, meaning that x here doesn't belong to a. Okay, x here doesn't belong to a. Okay. Okay, so okay, I just use this part. Okay, I just use this one. X not element of x is element of a complement. Okay, meaning that x doesn't belong to a. Okay, of course, such a function. Okay, such a function with these two values. Okay, 1 and 0. Okay, given that 1. Okay, if x is belong to a, and 0 if x is belong to a complement, meaning that when x belong to a complement, meaning other meaning that x here doesn't belong to a. Okay, of course, such a function here we call it as a indicator function. Okay, always remember when we talk about indicator function here, okay, this is the definition. Okay, meaning that this indicator function will take only two values, 1 and 0. Okay, 1 if this condition, 0 if this condition. Okay, meaning that if your function here takes two values, okay, but not 1 and 0, so we will not say that this function is is not indicator. Okay, for example, okay, so if from this function, let's time with 2. Okay, for example, I will time with 2. Okay, 2 times this function. Okay, so what the meaning of 2 times this function here? Meaning that, okay, so since we have two values here, 1 and 0, meaning that 1 here we times with 2, so we will have 2 here, and then 0 times with 2, we have 0. Okay, so now such a function that 2 times with this indicator function will give me will give us these two values, but these values is 2 and 0. Okay, when you have the values of 2 and 0, meaning that this function is not indicator. Okay, it's not indicator function. Okay, why? Because to be an indicator function, meaning that the function here should be take two values, which is 1 and 0. Okay, with the condition that this condition. Okay, so if you have such of function, we call it as a indicator function. Okay, for example, another example. Okay, let's consider this function. Okay, let's consider that second example. Our x is the set of real numbers. Okay, our x is the set of real numbers. Now I will define such a function fx. Okay, fx here is defined by this function. Is given by this value. 1 if 1 if x, 1 if x is element of the set of all irrational number, and 0 if x is element of the set of all rational number. Okay, so let's consider the second example. I will define such a function here that map from real numbers to the set of real number. Okay, so given that this one equals to 1 and this one equals to 1 if x element of I, and this one equals to 0 if x is element of q. Okay, you can see, okay, from this function, okay, so you see what do you mean of this function? Meaning that if your x here is an irrational number, then it's equals to 1. If x here is a rational number, then this function is equals to 0. Okay, and then from this part, you can see x is element of I, x is element of q. So from q here, I can write as what? From q here, actually I can write this one as I complement. Okay, I complement. Okay, because I complement, of course, I complement. What do you mean of I complement here? Meaning that R difference I. When R difference I, so I will have the set of rational numbers. So I can write this one as this one. Okay. Okay, so therefore, such a function here is indicator. Right? Why? Because this function takes two values, 1 and 0. Okay, so 1 here, if 1 here, the condition here say that the function is equals to 1 if my x is element of I. And then the second one is equals to 0 if my x here is element of I complement. What the meaning of x is element of I complement? Meaning that my x here doesn't belong to I. Okay, doesn't belong to this set. So therefore I can write, since this one is my indicator function, so since this function is indicator, so I can write this my fx is equals to this one. Okay, of course x side x. Okay, so this one. Okay. Okay, same. Okay, because this one also is given by this one. Okay, I can say that this one is actually same. Okay, now I can write this one. Okay, so this one. Okay, so this is a indicator function. Okay, of course indicator function where this become I, the set of all irrational number. Okay, and we know that our I here is subset of I. Okay, so this one. Okay, so this is a two example that I show you. Okay, so how so what's the difference between indicator function and also non-indicator function? Okay, meaning that when you consider indicator function, the definition is this indicator function takes two values, which is 1 and 0, with this condition. Okay, with the condition that the function is equals to 1 if x is element of A, and equals to 0 if x is element of A complement, or x doesn't belong to A. Okay, so now meaning that we can write this indicator function. Okay, so consider that x here is our set x, so this function have two values 0 and 1. Okay, 0 and 1. Okay, the values is only take 0 and 1. Okay, of course my A here, my A here should be subset of x. Okay, so this one. Okay, in many application, even in the theory of probability, I think you already discussed about this indicator function in that course. So of course this function have many application, even have been used in a wide practical wide application in the theory of probability. Okay, so this indicator function. And today we want to discuss some theorem. Okay, some theorem discuss about measurability of this indicator function. Okay, of course when we consider indicator function, let be our indicator function here. What I meaning that we discuss about the measurability of indicator function here. They have some properties discuss. Okay, they have a theorem discuss about measurability of this indicator function, meaning that our indicator function here can be measurable and also can be non-measurable. Okay, at the moment we just consider that our indicator function here can be any. Okay, can be any, meaning that we will not consider such of indicator function here is measurable. Okay, and we are not consider that our indicator function here to be non-measurable. Okay, let be any indicator measurable here. Okay, okay, so now theorem. Okay, theorem. So now we want to find, we want to consider such of indicator function here to be measurable. Okay, to be measurable. Okay, so now we have a very interesting theorem here. Okay, such of theorem say that such of indicator function here, okay, is measurable. Okay, if and only if, okay, of course our A here should be element of algebra. Okay, element of algebra. Okay, so meaning that in this theorem say that to have such of indicator function here to be measurable. Okay, meaning that they need to satisfy one condition. Okay, such of indicator function here is measurable, need to satisfy one condition, that our A here should be element of algebra or sigma algebra. In other words, okay, or we can say otherwise, okay, if our A here is not element of algebra, okay, if A is not, okay, if A is not element of our algebra, then, okay, then our indicator function here is not, okay, it's not measurable. Okay, of course it's not measurable with respect to this algebra. Okay, this algebra. Okay, because of what? Because theorem here say that if and only if. Okay, if and only if here meaning that it can be both side. Okay, it can be both side. So for example, you have this indicator function, and then you have a algebra. Okay, you have a sum algebra, and then you see that our A here is element of that algebra. Then it follows that this indicator function is measurable. Okay, by looking this subset. Okay, by looking this subset, is it element of algebra or not? Then it follows that our indicator function here is measurable or not. Okay, okay. So this is very nice theorem that discuss nice properties of measurability of this indicator function. Okay, okay. So later I will show you the example. Okay, an example. But before that, let's prove, okay, this theorem. Okay, let's prove this theorem. Let's prove this theorem. Okay. Okay, proof. Okay, of course, to prove that our indicator function is measurable, it should be satisfied the condition in the definition. Okay, in the definition. Okay, meaning that from the definition, if you consider all borrow set, okay, all borrow set here, okay, of course, then you find the pre-image. Okay, the pre-image of all borrow set. Okay, the pre-image of all borrow set should be inside of your algebra or sigma algebra. Okay, so this is the condition from the first definition. Okay, okay, to have that our indicator function here to be measurable, meaning that it will satisfy this condition. Okay, of course, let's first discuss about the pre-image of all borrow set here. Okay. Okay, of course, before that, okay, since our indicator function here takes two values, 1 and 0, okay, let's look all possible inverse, okay, inverse of this function. Okay, so meaning that, so now we will have we have x here takes two values, okay, 0 and 1. Okay, so meaning that if I consider inverse of, okay, since we have a 0 and 1 here, let me consider 0 first. Okay, so let's consider this one. Okay, what's the inverse function of, okay, this 0? Okay, okay, what do you mean of inverse here? Okay, meaning that inverse here we consider such of mapping. Okay, this one should be mapped from R to X. Okay, okay, so what is the inverse of 0 here? So inverse of 0 here is A complement. Okay, and then we have the inverse of 1. Okay, because the function here takes two value. So what is the inverse of 1? So this one we will have A. Okay, we will have A. Okay, of course, if we consider any, okay, any number y, okay, from this one, okay. So meaning that we consider such of value that different than 0 and different than 1, okay. So what I can say about this one, okay, inverse of y here. So since our function here doesn't take any values than 0 than 1, so this one is anti-set. Okay, this one is anti-set. Okay, of course our y here it's not equals to 0 and 1. Okay. Okay, so now, okay, now since we have, okay, so we have this part, so it's very easy now, okay, to find this p-image for all border set, okay, for all border set, okay, for all border set, okay. Okay, so since we have 0 and 1 here, we have two values, meaning that we can consider 4 types of border set, okay, 4 types of border set, okay. Of course, if I consider my B here doesn't contain 0 and doesn't contain 1, okay. If my border set here doesn't contain 0 and my border set here doesn't contain 1, of course this one is empty set, okay. Because of what? Because since our value of our indicator function here is 0 and 1, of course border set without 0 and 1 here, so we don't have any p-image, so we have empty set, okay. Next, if my B here is element of 1, okay, okay, let B here is element of 1, and but our border set here doesn't belong to doesn't contain 0, okay. If B here is contain 1 but B doesn't contain 0, so this one, okay, what do you mean of this one? So now our border set here we have 1, okay. So meaning that if you find a pre-image of border set that contain 1 but doesn't contain 0, it will be equals to this one, okay. It will be equals to this one, so this one will be equals to A. And if I consider the such of border set here contain 0, okay, contain 0 but doesn't contain 1, so this one will be A complement, okay, equal to this one. So lastly, we consider such of type, okay, such type of border set that contain both 0 and B contain 1, okay. So meaning that we have something like what? Okay, so we will have something like pre-image of inverse of this one union with inverse of this one. So we will have A union A complement. So this one is actually equals to X. Okay, A union A complement. So this one is equals to X. Okay, equals to X. Okay, so this is a pre-image. Okay, pre-image for all border set. Okay, when we consider such a function here is indicator function. Okay, so this one. Okay, so now we already find pre-image of all border set. Okay, so now we want to prove. Okay, we want to prove our theorem here. Okay, we want to prove our theorem here. And since we have a if and only if, what do you mean of if and only if here? Meaning that you need to prove both sides. Okay, from the first to second. Okay, and then you need to prove from the second to first. Okay. Okay, first statement. Okay, let's prove the first statement here. Meaning that X A here is measurable. Okay, if A here is element of F. Okay, one of F. Okay, meaning that our A here should be element of algebra here. Okay, so for the first statement here, okay, of course, straightforward. It follows straightforward. We can see that if X here is measurable, then our A here is element of F. Why? Because from the definition, okay, from the definition, we say that our function here is measurable if if we check the pre-image of all borrow set here should be element of F. Okay, since we say that our x here is measurable. Okay, when this indicator function is measurable, it satisfies this condition. Okay, from the definition, then from here straightforward we can say that our A here should be element of F. Okay, A here element of F. Why we say that A here is element of F? Because from this pre-image we can find our A here. Okay, we have our A here. Okay, one of a pre-image of our function here. Okay, so we have A here. Okay, so meaning that it follows that our A here is element of F. Okay, so this is the first one. Okay, and then the second one. Now we need to show that if my A here is element of F, okay, then our x here is measurable. Okay, so how to show the second statement here? Okay, so you see now now we have the pre-image. Okay, we already found the pre-image of for all borrow set here. Okay, from this pre-image we have 4. Okay, we have 4 after we consider 4 types of borrow set here. Okay, so from here it follows that, okay, of course empty set here is always element of algebra. Okay, why? Because the definition of algebra here say that the algebra here should be contain empty set. Okay, so straightforward we see that empty set here is element of algebra. Even empty set here is element of all algebra. So it follow. Okay, so we can see that empty set is element of F. Okay, another thing we see that our x here also is element of algebra. Okay, from the definition. Okay, and A here. Okay, from the second statement here we say that our A here should be element of F. Okay, A here should be element of F. Okay. Okay, so now how we come to this part that this indicator function here is measurable. Okay, if our A here is element of F, then this indicator function here is measurable. Meaning that to get this part that say that indicator function is measurable, meaning that it also should be satisfied condition to be measurable. Meaning that you see you need to show that the pre-image of all borrow set here is element of F. But now we have already already found that this empty set A and X here is element of F. So we miss this part. Okay, we miss this part, A complement here. Okay, so meaning that we need to check either this A complement here follows element of F, yes or no. Okay, so if A complement here also follow that is element of our algebra, so we can see that the pre-image of all borrow set here is element of algebra, then this part is true. Right. But if this A complement is not belong to F, okay, I already discussed from the previous our previous discussion. If we found that at least one, okay, pre-image that doesn't belong to F, therefore our function here is not measurable. Okay, so now let's check this A complement. Okay, so let's check complement here. It's either element of algebra. Yes or no? Okay. So now, A complement. Okay. So what the meaning of A complement here? A complement here meaning that we will have X difference A. Right. Okay. X difference A. Okay. By the definition, A complement is equals to X different A. Okay. So you see, X is element of A. A also is element of A based on our statement here. A is element of A. Okay. So what you can say about X difference A here? Is it element of F Sorry. So this one is element of algebra. A here also is element of algebra. Okay. Since our statement here, A here is element of algebra. So since we have X element of algebra, A also element of algebra, what you can say about this X difference A? Of course, X difference A also is element of algebra. Okay, why? Because from the definition of algebra here, it should satisfy, if you remember, it should be satisfy all condition that close under, it should be satisfied. The first empty set and X should be element of F. The second condition that our F here is closed under all set operations. Okay, what the meaning that our F here is closed under all set operation, meaning that our algebra here is closed under union, closed under intersection, closed under difference, okay, and also closed under symmetric difference. Okay, so you see X difference A, since X is element of F, A here is element of F, of course X difference of A here is element of F, because F is closed under difference operation. So meaning that from here I can say that A complement also is element of F. Okay, so this one is also element of F. So now you see from this pre-image, okay, pre-image for all borrow set, okay, so we will have, we can see that all of it is element of F. Empty set element of F, A here element of F, AC is also element of F, X also element of F. Therefore, the second statement also true. Okay, first statement true, second statement also true. Therefore, the theorem is proven. Okay, the theorem is proven. Okay, because the theorem say that our indicator function is measurable if and only if our A here is element of F. Okay, so when you have a if and only if here, meaning that the both statement is true. Okay, when you say that X is measurable if A element of F. Okay, true. And then if you then you say that if A here is element of F, it follows that the indicator function is measurable. Okay, true. From our proof is true, both sides. Okay, therefore our theorem is proven. Okay, our theorem is proven. Okay, so this is the how we can prove this theorem. Okay, and like I said just now, this theorem is talking about measurability of our indicator function. Okay. Okay, so now let's consider example. Okay, how we can understand this theorem. Okay, let's consider the simple one. So now let's consider the set with 3 elements. Okay, the video is recording, still recording. Okay, good. Okay, so now I will have this. Okay, from this the set of 3 elements here, I can consider 5 algebra. Okay, 5 algebras. Okay, let me the first one, intercept and X. Okay, F2 here is power set of X, and then F3. Okay, so we have empty set X, A, B, C. F4 is set X, B, A, C. Okay. F5 is set X, C. Okay, A, B. Okay, so okay, let's consider this. Okay, so now let's consider one example. For example, let's consider such of A here, subset of X. Okay, so let's choose my A here is this one. Okay, AC. Okay, let me AC here. Okay, subset of X here, that AC. Okay. Okay, so now, okay, how we can define such of indicator function here? Okay, let be AC. Okay, AC, and then I will have X here. Okay, of course, this one is equals to what? Okay, this one is equals to 1 if my X here is element of this subset. Okay, AC. Okay, AC here. And then this one is equals to 0 if, okay, my X here is element of A complement. So what do you mean of A complement here? A complement here means that we have X difference AC, so this one is equals to B. Okay, it's equals to B. Okay. So meaning that from this indicator function, we will have if X here is equals to A. Okay, if X here equals to A, of course this function is equals to 1. Why? Because A here is element of this subset. And if X here equals to B, equals to 0. Okay, why? Because B doesn't belong AC here. Okay, therefore it's equals to 0. And if X here equals to C, this function equals to 1 because C is element of this subset. Okay, so you have this one. Okay, so now let's find, okay, after this let's find the pre-image. Okay, let's find the pre-image of all borrow set. Okay, let's find the pre-image of all borrow set here. Okay, let's find the pre-image of all borrow set. Sorry. Okay, okay, pre-image of this one. Okay, of course. Okay, so this one, since the pre-image, okay, since we have the two values 1 and 0 here, so I can say that this one equals to empty set if my B here doesn't contain 0 and doesn't contain 1. Okay, and then if my B here, okay, contain 1 but B here doesn't contain 0. Okay, so you have 1 here, right? Okay, 1, so we have AC. Okay, so we have AC. And then if B here contains 0 but B doesn't contain 1, so we have 0 here, then we will have AC complement. AC complement is equals to B. Okay, and then if B here contains 0 and B here contains 1, so meaning that we have both 1 and 0, so we take B union AC here, so this one will give me our X. Okay, so okay, X. Okay, so now you see. Okay, so now let's check. Okay, let's check. This indicator function is measurable with which algebra? Okay, with respect to which algebra? Okay, of course F1 not. Okay, so F1 not, meaning that our indicator function here is not measurable with respect to F1. Why? Because in our AC here, okay, it's not belong to F1. Okay, so it's not measurable. Okay, so not measurable here. Okay, let's check for F2. Okay, you see empty set, element of F2. AC is element of this algebra. B is element of this algebra. X is element of this algebra. Meaning that when you consider all pre-image of, you consider pre-image of all borrow set here is element of this power set. Okay, it's element of this algebra. Meaning that, okay, our indicator function here is measurable with respect to second algebra. Okay, so let's look F3, the third algebra here. Okay, so this function, is it measurable with respect to this algebra? Okay, so empty set we have. AC, do you have inside of this algebra? No. So you don't have AC. Okay, so this indicator function is not measurable with respect to third algebra. Okay, how about the F4 here? Okay, how about the F4 here? Okay, F4 here, so you have empty set, you have AC, you have B, and you have X. Okay, so therefore, this indicator function is measurability. This indicator function is measurable with respect to fourth algebra. Okay, next F5 here. So empty set you have AC. Do you have AC here? No, right? Okay, when you don't have AC inside here, so you show that at least one pre-image here doesn't belong to this algebra. So this indicator function is not measurable with respect to this algebra. Okay, so to conclude, okay, so such of indicator function here is measurable with respect to second algebra and fourth algebra. Okay, second and fourth algebra. Okay, so you can see here, okay, how we can apply this theorem. Okay, how we can try to understand the theorem here. Say that, okay, the theorem say that such of indicator function is measurable if and only if this A, okay, this subset here AC should be element of algebra. Okay, should be element of algebra. If and only if, meaning that if our subset here is element of algebra, okay, then it follows that our indicator function here to be our indicator function is measurable. And you see F1 is it contain AC? No. F2, do you have AC in F2? Yes. Do you have? We have. Okay. So F3, do you have AC here? No. F4, do you have AC here? Yes. Right. Okay. F5, do you have AC here? No. Okay. No. So meaning that from this list of algebra, you see that our AC here only inside in second algebra and also fourth algebra. Okay, for the first, third, and fifth algebra, we don't have this AC. Okay. So from the theorem say that if our AC here, okay, if our AC here is element of this algebra and this algebra, then it follows that our indicator function here is measurable to these two algebra. Okay, why this indicator function is measurable with respect to these two algebra? Because these two algebra contain AC. Okay, this subset. And this indicator function is not measurable with respect to first, third, and fourth algebra. Why? Because this AC doesn't contain in F1, doesn't contain in F3, and doesn't contain in F5. Okay, so this is theorem. Okay, how we can understand this theorem. Okay, so this theorem meaning that what I can say, this theorem have a very interesting properties. Meaning that if you want to check your indicator function here is measurable or not, just check the condition that such of subset here, is it inside of that algebra or not. Okay, meaning that okay, of course this one I just want to show you how we can understand the theorem, meaning that I just provide you the pre-image of all border set here. Okay, but if you can understand and you can see clearly about this theorem, you don't need to consider this pre-image. Okay, you don't need to find the pre-image of all border set here. Because of what? Because the theorem here is very easy to it's very easy for you to check either your indicator function here is measurable or not, just looking that this subset, is it element of algebra or not. Okay, or is element of that algebra or not. Okay, if this subset is element of that algebra, meaning that this indicator function is measurable with respect to this algebra. Okay. If AC here is not element of that algebra, meaning that this indicator function is not measurable with respect to that algebra. Okay. Okay, let's consider the second example. Okay, very fastly. Okay, very fastly we consider the second example. Okay, let's consider this one. let's consider this example. Okay, let's consider this example. B. C. Okay, C. Okay, such a function here. Okay. Okay, let's check. Okay, let's check this function here. Okay, this indicator function here is measurable with respect to which algebra? Okay. Okay, since the theorem say that such of indicator function here is measurable if and only if my C here, okay, this one is a subset here, should be element of our algebra. Okay, so now we just need to check which algebra here contains C. Okay, which algebra here contains C here. Okay, F1. Does it F1 contain C? No. Okay, no. So meaning that our indicator function here is not measurable with this algebra. Okay, how about the second one? Does it, the second one here contain C? Yes. The power set of X here contains C, right? Okay, so meaning that this indicator function is measurable with respect to this algebra. Okay, so now let's check for third algebra here. Does it, the third algebra here contain C? So we don't have C. Okay, we don't have C, meaning that this indicator function doesn't, this indicator function is not measurable with third algebra. So F4, does F4 here contain C? No. So it doesn't contain C, meaning that this function is not measurable with respect to fourth algebra. So fifth algebra, does it have C here? So you have C, right? Okay, so you have C here. Okay, in this fifth algebra, meaning that this indicator function is measurable with respect to fifth algebra. So from this theorem follows that this indicator function is measurable, okay, with respect to second and fifth, okay, algebra. Okay, second and algebra number 2 and also algebra number 5. Okay, because of what? You see, the second algebra here, you have C, okay, and then the fifth algebra also you have C, right? So straightforward by this theorem, you can say that this indicator function is measurable with respect to second and fifth algebra. And of course, this indicator function is not measurable with respect to first, third, and fourth algebra. Why? You say first, third, and fourth algebra here doesn't contain C. Okay, you don't have C here. Okay, okay. So this is a very nice properties. Okay, nice theorem. Discuss about the measurability of indicator function. Okay. 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 So next discussion. Okay. Next discussion. Okay, so for the next discussion, okay, so I would like to discuss about second theorem. Okay, second theorem. Second theorem here is talking about very nice properties of measurable function. Okay. Okay, before that, okay, let's consider some example. Okay, some example. Okay, so I want to show you from this example why we have a sum problem to prove that this function is measurable. Okay, is measurable by the first definition. Okay, and then how we can outcome, okay, this problem. Okay, when you have a sum function and then you have a difficulty to prove that this function is measurable, okay, and then of course to prove such a function here is very difficult because very difficult to use the first definition because of the problem that I will show you, okay, in this example. And then next we want to discuss, okay, how we can solve this problem, okay, how we can overcome this problem, okay. When you have a problem to prove such function is measurable, it's very difficult to use the definition number one, okay. So but then we can show that this function is measurable by using this second theorem, okay, this second theorem. So this second theorem I will present later, okay. Okay, for example, if I consider example, okay, let me, okay, now I will consider such of set here, okay, A, B, C, D, okay. Okay, let me the set here have a 4 elements, okay, Okay, so now, okay, let's consider a function here, okay, let be FA, okay, for example, FA is equals to FD, okay, is equals to true, okay, is equals to 2, okay, let be FB is equals to, okay, FB is equals to 3, okay, let be FC is equals to 4, okay, for example. Okay, I will define such a function here that map from X to the set of real number 2, 3, and 4. Okay, of course from here I can say that my fx is equals to this one. Okay, 2, 3, and 4. Okay, so you have 3 values of this function. Okay. Okay, of course to check our function here is measurable or not. Okay, we want to check our measurable function. Our function here should be measurable, meaning that we need to consider, we need to find the pre-image of all Borel set. Okay, the pre-image of all Borel set. Okay, of course, since our function here we have 3 values. Okay, we have 3 values here, meaning that, okay, what do we have if we have 3 values here? So now we will consider 8 types of Borel set. Okay, when we have 3 values, meaning that we have 8 types of Borel set. Okay, what is the what the 8 types of Borel set here? Meaning that I will consider such a Borel set here, a Borel set that doesn't contain 2, doesn't contain 3, and doesn't contain 4. Okay, and then next I will consider such a Borel set here contain 2, but my B here doesn't contain 3 and 4. Okay, so this one. So and then I will consider my B here, the third types of Borel set. I will consider Borel set that contain 3, but my B here doesn't contain 2 and 4. Okay, so next I will consider such a Borel set that contains 4, but my B here doesn't contain 2 and 3. Okay, 2 and 3. Okay, and then I will consider such of types of Borel set that contain 3 and 4. Okay, but my B here doesn't contain 2. Okay, and then I will consider such of type of Borel set that contain 2 and 4, but B here doesn't contain 3. Okay, and then I will consider such of another types of Borel set that contain 2 and 3, but B here doesn't contain 4. Okay, and then the last one I will consider such of types of Borel set that contain all of this value 2, 3, and 4. Okay, so this one. Okay, so this one is from your previous home task. Okay, I already asked you to just to find, okay, the pre-image of all this Borel set, and then try to check this function is measurable with respect to which algebra. Okay, so this is okay, for example, this function here. Okay, I will consider, okay, so we will have 8 types of Borel set that you need to consider. Okay, 8 types of Borel set that you need to consider, meaning that you will have 8 pre-image here. Okay, 8 pre-image here. Of course, 8 pre-image here, you need to find. Okay, you need to find by yourself. Okay, you need to find by yourself. Okay, and then after we find all the pre-image of this one, okay, all pre-image of all Borel set here, then we need to check this all. We need to check all pre-image of all Borel set here is element in which algebra. Okay. Okay. So this one, if we have a value that if we have function with 3 values, okay, meaning that we need to consider 8 types of border set here. Okay, 8 types of border set. Okay, so now comes to very big problem here. Okay, so now very serious problem. For example, if I consider such a function here, okay, now my function here have 4 values. Okay, my function here have 4 values. For example, I have 2 here, and then let be fd is equals to 5. Okay, so I have 4 values. Okay, meaning that my function here takes 4 values, 2, 3, 4, and 5. Okay, so I will have 4 values. Of course, when I consider the pre-image of all border set, okay, pre-image of all border set here. Okay, so since we have 2, 3, 4, 5 here, okay, 2, 3, 4, 5 here, okay, we have 4 values here, okay. So if we have 3 values, meaning that we have 8 types of border set that we need to be considered. Okay, then if we have 4 values here of our function, meaning that we need to have 16 types of border set. Okay, border set need to be take as a consideration. Okay, so we have 16. 16 meaning that what? Meaning that you need to consider B here doesn't contain all of it. Okay, doesn't contain this number 2, 3, 4, 5. Okay, then we will consider such a border set that contain 2 but doesn't contain 3, 4, 5. Okay, and then so you okay, meaning that you consider border set contain of 3 but B doesn't contain 2, 4, 5, and then you consider border set, such of type of border set that contain 5 but B doesn't contain 2, 3, 4, and then you will consider such a border set that contain 2 and 3 but B here doesn't contain 4 and 5. Okay, and then so on. Okay, you consider such of B here contain 2 set here, and then the last one. Okay, and then you will consider B here contain 2, 3, 4. Okay, but B doesn't contain 5. Okay, and then you will consider the whole thing here that B contain 3 elements. Okay, all possible here, and then the last one you contain that B here contain all this number 3, 4, and 5. Okay, so meaning that, okay, if you complete this one, okay, if you complete all types of border set here, meaning that you have 16. Okay, you have 16 times of border set, meaning that from these 16 types of border set you need to find 16 pre-image. Okay, 16 pre-image. Okay, so they quite a lot of number, and of course if you consider X here have more than 4 elements, okay, for example I have A, B, C, D, E, of course you can define more than 4 values, okay, meaning that at maximum maybe you can define 5 values of the you can define function with 5 values. Okay, okay, so you can consider you can define, okay, a lot of values, okay, for your function. Okay, of course when the values of function here is increased, then the types of the border set here of course will be increased. Okay, when will be increased, meaning that so now it's very difficult for you to find the all pre-image here. Okay, you need to find the all pre-image here when the values of function here is increased. So of course the pre-image also will be increased, and then it's very difficult for you to difficult for you to find this all pre-image. Of course, if your function here have one value, it's easy for you to use this first definition. Okay, because when you have only one value, meaning that you only have 2 types of border set. Okay, so it's easy. And then if your function here have 2 values, okay, if your function here have 2 values, still easy for you to check the measurability of that function by using the first definition. Okay, because when you have two values here, then meaning that you only have 4 types of border set. Okay, still you can find the pre-image of all these border set, pre-image of all border set here. Even if you have values of 3 here, okay, you have a function with 3 values here, still easy for you to find the pre-image of all border set here. But now you see the number of pre-image here increase to 8, okay, from 2, 4 and 8, okay. And then of course if you consider 4 here, okay, 4 values here, then they start increase to 16, okay. And then 5, they start increase to 32, okay, 32 types of border set and so on. So it's very difficult for you to check to check the measurability of function that have many values, okay, because your border set here, the types of border set here start increase and start increase. So it's very difficult for you to find the pre-image of all border set here, okay. Okay, so how we can outcome this problem? Okay, for example, if you have a function with 5 values or 6 values or 7 values and so on, okay, so we want to check the measurability of this function. Okay, of course it's very difficult for us to check by first definition. Okay, it's very difficult for us to check for the first definition, so meaning that we need to have another method to solve such problem here, okay. Okay, so therefore we will have another theorem. Okay, this second theorem. Okay, without proof. Okay, just formulate this theorem without proof. Okay, we just use this theorem. Okay. Okay. So. Okay. Okay. Theorem. Okay, theorem. Okay, so maybe I stop first, okay, because already 5:30 AM. Okay, already 5:30 AM. So maybe around 50 minutes we okay, it's okay. I just stop for a while this video. Okay, and then I will continue this theorem, and then I will show you some example around another 30 minutes, because we now the time is 5:30 AM. Okay, I'm doing this video around 4:30 AM 4:30 AM just now. So maybe okay, I stop first here. Okay, after Fajar prayer, okay, I will continue another 30 minutes to discuss this theorem. Okay, of course, first of all, let's consider. Okay, I just write first what's the theorem here say. Okay, of course, a function, okay, is measurable. Okay, a function, okay, meaning that a function here is measurable. Okay, if and only if, okay, for any real numbers here, okay, for any real numbers here, then we can find the pre-image of this subset. Okay, we can find for this we can find the pre-image of this subinterval should be element of sigma 0. Of course, what the meaning of this one? Meaning that, okay, a function of measurable function, a function here is measurable if and only if it satisfies this condition. Meaning that if you consider all values from real number, okay, any a here means that you consider all values of real numbers here, then you can find the pre-image of all real numbers here is element of sigma 0. Okay, because what the meaning of pre-image of this subinterval? Meaning that we need to consider the pre-image of all subinterval, this subinterval, where our a here it takes all value of my real numbers. Okay, and then if I have a pre-image of all these sub-interval is element of our algebra, then we say that our function here is measurable. Okay, I will stop first at this time. Okay, after Fajr prayer I will continue. Okay, around 30 minutes. Okay, to show you some example. So how we can use this theorem to overcome this problem. Okay, so for a while I just stop first. Okay.